So now continuing on with our theme of discussing formation scenarios for UDGs, Tim Carleton from UC-HiPACC.
Hello, thank you. So like I said, I'm going to be talking about a formation mechanism for UDGs that involves tidal stripping as these UDGs pass through a cluster environment. And this is ongoing work that I'm doing with some collaborators, Rafael Rani and Jorge Penrubia at Edinburgh, as well as Mike Cooper and Manoj Kaplinghat at UC Irvine. All right, so I would say thank you for all the previous talks to give a great introduction and motivation to understanding UDGs. And as many people have pointed out, understanding the dark matter halos that host UDGs will go a long way to understanding their formation and evolution. For example, Mandoka et al. 2016 measured this high mass to light ratio in UDG in the coma cluster, pointing to some formation mechanism that these UDGs are somehow failed Milky Way galaxies. But then there's also some measurements that previous talks have touched on that suggest that this is not always the case, that many UDGs may be in smaller mass halos. For example, this work from Sifon this year using weak lensing measurements to show that the average halo mass of a UDG is probably not Milky Way 10 to the 12 solar masses. But I would argue that understanding the environments will also go a long way to understanding the UDG formation and evolution. Both these works have been pointed out previously that UDGs were first identified in massive clusters. And it appears that while there are UDGs in the field, there's a huge population of UDGs in the cluster. And the abundance of UDGs relative to the abundance of brighter dwarf galaxies increases with increasing cluster mass. So this, to me, suggests some effect of environment on the UDG population. Yes. So to kind of understand how this environmental mechanism may be involved with, we thought would be involved with tidal stripping of typical dwarf galaxies. And so to understand how we can get a UDG by tidal stripping of dwarf galaxies, we used some great work by Irani 2015 that showed the change in the stellar mass and half-light radius of a dwarf galaxy that's undergoing a tidal interaction can be showed to follow these tracks dependent only on the amount of mass loss by the satellite halo, with the caveat that this depends on the inner shape of the profile that the galaxy lives in. So you have, if you're in a cuspy dark matter halo, you're not experiencing a significant amount of, a significant change in your stellar radii, regardless of how much mass you lose. Whereas if you're in a core dark matter halo and you lose about 50% of your mass, your radius can expand by over a factor of 2. And so this gives us a really powerful tool to investigate how the properties of dwarf galaxies will change as they fall into a cluster and experience the tidal effects of the cluster. And we decided to look at how this can produce UDGs that we observe in cluster environments. And so to do that, we went into the Bolshoi simulation and picked out a coma-like cluster object and tracked the subhalos that are in the cluster now back to their infall, and followed the orbits of those subhalos and measured the amount of mass loss that, determined the amount of mass loss that they experience and the change in the properties of the stellar mass and half-light radius that they experience as a result of those tidal interactions. And if we start them off on the dwarf elliptical size-mass relation from the gamma survey shown in blue, and evolve them according to these tidal tracks, we see that galaxies in cuspy dark matter halos don't produce a significant number of UDGs, but galaxies in core dark matter halos do produce do span the large UDG space that's populated by UDGs in the coma cluster, shown as the red squares here. And so this model seems to work out nicely in that we're getting a lot of UDGs formed in 10 to the 10-ish solar mass dark matter halos, where observations of galaxies in the field find core dark matter halos that would experience the significant tidal effect as they pass through the cluster. And so just another way to look at this is just looking at the size distribution of UDGs formed in core dark matter halos, shown as green, and cuspy dark matter halos, shown as purple, compared with the observed size distribution of UDGs in coma, shown as red, and a few low Z clusters from Vandenberg 2016, shown as this black line. And what you can see is that this formation mechanism of forming UDGs through tidal stripping of the dark matter halo is able to reproduce the largest UDGs that are observed in clusters for galaxies in core dark matter halos. So I just want to kind of, as I'm putting up my conclusions, emphasize that that this model can give us a good prediction for the stellar velocity dispersions that we should observe in a large population of UDGs on the order of 15 to 25 kilometers a second. While it's not on the level of Dragonfly 44 with this high velocity dispersion, it's a little bit higher than the average stellar velocity dispersion at that given stellar mass, because you're measuring, if you're using the stellar velocity dispersion to measure the mass, it's at the half-light radius, and there's a significantly more mass within the large half-light radius in these halos. And so we're able to produce these UDGs, and we're looking to expand on this work to using the ELVIS simulations to investigate the properties, the effects that tides have on local group satellites, and in particular ultrafaint dwarfs. So, thank you. No, so our model does not do anything for UDGs in the field. It does not preclude any model that forms UDGs in the field. We can have UDGs form in the field through some other mechanism that, whether it be feedback or whatever, that can exist in the field, but our model says you do produce a significant number of UDGs in clusters simply because of this tidal stripping.
So maybe I missed it, but how do you relate Galaxy the radii to your tidal radius?
So the starting half-light radii of our galaxies are, we just use abundance matching to get the stellar mass of the galaxy and use the observed stellar mass size relation to get the starting half-light radii of the galaxy. We don't consider, we're looking into considering some more sophisticated models for relating the size of the galaxy to the dark matter halo, but that's what we've done so far.
So you, from abundance assume some stellar mass distribution.
So the distribution of, we get the distribution of halo masses from the Bolshoi subhalos and then use abundance matching to produce the stellar masses that would be falling into that.
The size stellar mass relation from gamma.
Yeah, the size, yeah. Yeah.
All right, one quick final question from Victor.
Wait, so what are the sizes of the dwarfs you
It's around, it's set based on the scale radius of the halo is about a couple kiloparsecs for these, for the subhalos that we're seeing.
Let's thank Tim again. And